In the last video we looked at the time-dependent Schrodinger equation, and we kicked off by assuming this form for the wave function, a plane wave. I'm going to show in this video that this is not only an unacceptable solution when it comes to quantum mechanics, this is an idealization. Like frictionless surfaces in physics that we use all the time, it doesn't exist. This is an idealization. It's a mathematical idealization for reasons I'll get to in this video. So let's first of all think about the spectrum, the Fourier spectrum, the spatial frequency spectrum for a wave of this type. Okay, let's simplify this down a little bit. Let's just consider the spatial component of it. And let's write a simple, get rid of the complex part of it just for a second. We'll think about a cos k0x, which is the equivalent of our cos omega 0 t, which we looked at before. So our Fourier coefficients, you remember, I hope, the modulus square of the Fourier coefficients for a cos wave of this type, we'd have a spike at n equal to 1 and a spike at n equal to -1. So that's our Fourier spectrum. And this would be associated with spatial frequency k0, and this would be associated with the spatial frequency minus k0. So that's all well and good for a periodic function where we use our Fourier series. Our Fourier series gives us discrete coefficients, just gives us a list, n equal to 1, n equal to 2, n equal to 3, n equal to -1, n equal to -2, n equal to -3, etc. Question is, how do we represent a sine wave or a cosine wave, an infinitely extended sine or cosine wave, in terms of a Fourier transform? It's a continuous function. How do we, what is the Fourier transform of a sine wave or a cosine wave? It's got to, it only comprises one pure single frequency. So we need to find some function that somehow captures the fact that this is, an absolute, perfectly defined value of frequency, be it spatial frequency or temporal frequency. And to do that, we need to use a mathematical monster, which causes mathematicians a great deal of indigestion, called the Dirac delta function. Now over here, I actually have Dirac's Principles of Quantum Mechanics, which is a great book, and he describes, and I described this in the note, let me see if I can find it, there we go, page 58, page 58, the delta function. And he defines the delta function there. So what is the delta function? Well, the delta function allows us really to treat, as Dirac says, infinities, and allows us also to treat absolutely pure sine tones, absolutely pure waveforms that comprise just sinusoidal components that extend to infinity. So how does it do that? Well, let's just start with describing what the delta function is. And I'll tell you what, I will take it straight out of Dirac's book. And how Dirac defines it is, well, there are two equations. Let me get rid of this so we don't get confused. Two key equations here from Dirac's book. Okay, that's one, which already looks fairly strange, I'm sure. And the second one, and this is the more important one, and I'm going to take a liberty here just to keep consistency with the notes and with our labeling conventions and variable conventions. We've also got this, which is actually more important for what we're going to do. Two key equations. So we've got this thing called the delta function, and it's a function like no other. And it doesn't, for one thing, it doesn't make really any sense outside of this integration. This, for reasons we'll get to, is called the sifting property of the delta function. But what it looks like, let's see if I can get it over here on the board. let's do it here, is a function that looks like, and it's basically, we draw it like that. That's if we've got, and that will be delta x minus x naught. Or we could have it at the origin. That's a very wobbly origin. Or we could have it here. And then it would be delta x. Why is it drawn like a little arrow? Well, the best way of thinking about the Dirac delta function is in the limit of a top hat function, which we've covered at length, as we shrink and shrink and shrink that top hat function, but what we do is we keep its area equal to 1. So as it becomes narrower and narrower and narrower, it gets higher and higher and higher, until we reach the limit. And yes, I know this is difficult to swallow, but until it reaches the limit where it's infinitesimally narrow but infinitely high, and its area is 1, and the area still under the function is still 1. So to say that again, we have a top hat function, and in this case we'll have that also just for consistency with this. Our top hat function is at x0, and our top hat function is a wide. So when the limit of a going to 0, while keeping the area under the top hat equal to 1, what we end up with is our Dirac delta function. So you might think, why in the name of almighty Zarquon would you ever introduce a function like that, such an evil pathological function? Why did he do that? Well, for a number of reasons, but one of the key reasons is it allows us to answer the question, what is the Fourier transform of a pure sine function or a pure cosine function or a pure complex exponential? Without the delta function, we can't really answer that question. And given that Fourier transforms, as we've seen, are absolutely core to quantum mechanics in terms of connecting position and momentum, and in terms of connecting time and frequency, and later on we'll see time and energy, we really need to be able to determine the Fourier transform of a pure sine wave. We've done the Fourier series, as I said, and the Fourier transform is slightly different because the Fourier transform is a continuous function. And then if you've got a continuous function with the discrete value, how do you represent that discrete value of frequency? Spatial frequency or temporal frequency. And the way you do that is with the delta function. So let me explain a little bit more. So we have something whereby we integrate between these limits because delta x is 0, because the delta function is 0, everywhere else apart from at this particular absolutely defined position x0, when we take a function and multiply it by the delta function under this integral, and again the delta function really doesn't make sense outside of this integral, then what we do is we get the value of the function at the position of the delta function. So what does this mean? Okay, it looks complicated, but actually, if you're willing to swallow the delta function, and the idea of the delta function being a top hat function which we've squeezed and squeezed and squeezed until it's infinitesimally narrow and infinitely high, if you're willing to swallow that, this next bit's fairly easy. So let's say we've got a function f of x. It's arbitrary. Let's just take an arbitrary function. Looks like that. Not have it double on black. Okay. And okay, this is obviously your x-axis. And let's say we have our delta function here at x0. Now, the delta function is 0 everywhere else apart from at that position. So if we do this integral, if we take our function and multiply by the delta function and then integrate over the entire space, then because the delta function is only non-zero at this point, then basically what you're going to end up doing is sifting out, hence the sift, sifting out your values of the function until you get the value of the function at x0. I hope that makes some sort of sense. Now, I know delta function is something that traditionally causes undergraduates a great deal of conceptual pain. I understand why, but this aspect is I hope fairly straightforward, in that what you're doing is you're using the delta function to sift out and select a particular value of the function at x0, and just that value alone. And remember that the integral under this is 1. Integral, although it's infinitesimally narrow and infinitely high, it's the area under the delta function is 1. So when you do this integral, you multiply through, you're basically just getting this value of the function at x0. So you're pulling out f of x0. Alternatively, if you had your delta function positioned instead of delta x minus x0, if you had your delta function at the origin, which would just be delta x, and it's positioned here, then the value you get here would be f of 0, because your delta function is at the origin, is at 0. Here, it's at x0, so the value you'll pull out is f of x0. I hope that makes some sort of sense. But how does that then help us with the Fourier transform of a sine wave or a cosine wave? Okay, in essence, I'm going to work backwards here. Let's go back to I'm going to think about this for reasons which will become clear, rather than cosine k0x. But we've got a well-defined plane wave. Given that it's a plane wave with that well-defined spatial frequency, we would expect our Fourier transform really to only exist, or to only have value at that particular value of spatial frequency. We know that from the Fourier series, we just get these well-defined spikes. The delta function allows us to define that particular value of k0 when it comes to a continuous function like the Fourier transform. So we can write a Fourier transform of this and let's put a little arrow on it, and that's how we represent the delta function. So we are making the assumption that because that's got a well-defined spatial frequency, and because our Fourier transform is telling us about the spatial frequencies that comprise that waveform, that it's going to look something like this, where we've just got one single well-defined k0, which we define using the delta function. Let's check that. So how are we going to work out what... Let's get rid of this. And let's assume that we've got that Fourier transform. Question then is, how do we work out what the function is associated with that particular Fourier transform? To do that, we use something called the inverse Fourier transform. We've done the Fourier transform, which takes us from x to k, or from t to f. We can also obviously go in the opposite direction, going from f to t, or from k to x. It's the same mathematical process in essence. The formula is slightly different, but it's the same idea. We're going from space to momentum, and we can use a similar process to get back from momentum back to space again. And we call that, for hopefully obvious reason, the inverse Fourier transform. And so the inverse Fourier transform allows us to recover our function f of x, and it's written like this. You will see it expressed differently in terms of the placement of this constant. Don't worry about that. The important bit is what's happening in this integral. So we take our Fourier transform, which is this, and that's how, if you check back in your notes and look at the expression for Fourier transform, you'll see this is pretty much the same, apart from now our integration is over k, because that's what our function is over, our Fourier transform is over k, and we've got a positive rather than a negative in terms of the exponential here, in terms of the argument of the exponential function. Right, so we've got this Fourier transform. We want to now work out the function f of x that relates to this Fourier transform. So our f of k is just a delta function at that particular point. Right, so you've got that graph in mind. I'm just going to shift that graph, so a little bit of space. Actually, I'm going to put it over here. Let me put it over here, just so that you've always got this in mind. Okay, so that's our Fourier transform. So, f of x What's our Fourier transform? Our Fourier transform is a delta function located now. Remember the sift property of of delta functions. E to the I k0x. We sift through the function and pull out the value of the function at k0, which is the position of the delta function. That makes some sort of sense. So, give or take this constant, and it depends on how you define the Fourier transform, and as long as you're consistent between the inverse Fourier transform and the Fourier transform, it's fine. But give or take this constant, what we've got is a plane wave. E to the I k0x, which is our plane wave solution. Given that we started off saying what we wanted to do was show that the delta function at k0 represented the Fourier transform of this, by going in the opposite direction, we've effectively shown that. We've shown that for a complex exponential function, a Fourier transform is a spike, a delta function at k0. Okay, it's one more step before we get to the end of this video. It's a lot of maths. You might want to take a coffee, take a breather, pause. I am definitely going for a coffee after this one. So, I started off this video by saying that we had major problems if we use a plane wave as a representation of a particle. Major problems if we use a plane wave as a wave function in quantum mechanics. Two key reasons for that. Okay, let's see what those problems are. Let's just write our wave function like this. And let's just assume it's a straight plane wave. We've just seen, we know that the Fourier transform for that, and let's write that as a big psi as a function of k. We know that Fourier transform is that. So if we Fourier transform this, we get that. If we inverse Fourier transform from here, as we did just previously, we get back to that. All right and good. The issue is this. What's the modulus squared of that function, which tells us the probability? Well, the modulus squared of that function is 1. So, if we look at the modulus squared of our wave function as a function of x, it's flat across all of infinity. It's just a constant. We have absolutely no knowledge at all about the position of the particle. We've got infinite uncertainty, and hopefully that does not come as a shock, because our Fourier transform, or delta k, is infinitely narrow, which means our delta x, reciprocally related, has got to be infinitely broad. So, major problem, because to have this wave function means we have absolute infinite uncertainty in the position of the particle. We're completely certain as to the spatial frequency, wave number, wave vector, whatever you want to call it, but completely, infinitely uncertain with respect to the position. Moreover, right, that's bad enough. Moreover, the issue is this. Remember that for it to be a valid wave function, we have to be able to integrate the square of the wave function. It has to be square integrable. And if you think about, well, what's the integral of this? Well, you're just taking this area across all space, and if this is going from, if this is infinitely wide, because this is infinitesimally narrow, then we've got a problem because the integral diverges. So this is not a physically acceptable wave function. Which of course begs the question, well, how do we get out of this dilemma? What do we do to get a physically acceptable wave function if it's not a plane wave? As you might guess, Fourier is going to come to our rescue again. I'm going to get a coffee, you can go and get a coffee, and I will see you for the next video. Thank you.